Okay, great. My name is Pierre Albin. I'm from all over the place. I was born in California. I grew up in Texas and Mexico. I did my PhD in California, and then I worked in Boston, in New York, in Paris, and then here. The last novel I enjoyed was The Power by Naomi Halderman or something like that. Women all of a sudden acquire the possibility to shoot out electricity from their hands. It's very good. Okay, so what is algebraic topology? What is topology? So, topology starts in 1736 with Euler. So, like most things in math, it all goes back to Euler. And we usually name things after the first person after Euler to come up with them, because Euler already has enough things named after him. In this case, he started topology because he got a letter from a mayor of a town in Germany. And the mayor was telling him about Kennisburg and their bridges. So they have a river, and they have an island, and then there's like a peninsula. And then they had bridges connecting like so. And the letter claimed that every Sunday, the citizens would go on a walk around the town, and they would play a game where they would try to walk across all 7 bridges without ever repeating a bridge. And they hadn't been able to do it. And so this mayor wanted to know if Euler could figure out how to do it so he could impress his friends. And Euler wrote back a letter saying that no, that's not going to work. And he pointed out that, of course, we don't really care how long the bridges are. We don't care what angles. It's enough to know what things are connected. And so it's equivalent to trying to draw this figure without lifting the pencil or repeating an edge, right? And there had been other things like that. There was in medieval times, this was known as the devil's signature, because apparently the devil could sign it without lifting the pencil or repeating an edge. But anyway, Euler very quickly realized that the problem is that if you're going to do what we now call an Eulerian cycle, every time you go somewhere, you have to leave. So you need an even number of bridges, at least everywhere except for the initial point and the end point. And he proved that it's an if and only if. You can do it. You can draw without lifting the pencil or repeating an edge. If and only if every vertex has an even number. Come on in. You can sit here. If and only if every vertex has an even number of edges connected to it, except possibly for 2, for exactly 2, because you would need to start somewhere and end somewhere else, right? So he just wrote that in the letter, sent it back, and then he presented a paper to the Russian Academy, I think, talking about this problem and pointing out that it was sort of a new sort of problem. What he liked about it was that no area of math seemed to cover it. And he referred to this new type of math as geometry situs, or geometria situs. Where situs just means position. So the geometry of position. He cares about where things are located, but not about lengths or angles. And then a little while later, he came up with the Euler characteristic of a sphere, is how we interpret it. He noticed that every polyhedron satisfied vertices minus edges plus faces is equal to 2. And one thing that's really amazing about this formula is not just that Euler discovered it, but that nobody else had. Because people had been studying polyhedra forever, right? Plato talks about polyhedra. And despite that, nobody had noticed this. Descartes came extremely close. In fact, Descartes came extremely close to figuring out the analytic version of this, which is now known as the Gauss-Bonnet theorem. But he didn't. So one fun thing from here is if you want to look at the Platonic solids, so these are the polyhedra where every face has the same number of edges and every vertex has meets the same number of faces. So fun fact, if you get bored during the historical discussion, plug that in and prove that there are exactly 5 polyhedra possible with those restrictions. Right. The Greeks did know about these, but they did not have a quick proof that they were all of them. And Plato built these into his philosophy of the world, of how the world is shaped. The largest one, for example, was the heavenly sphere where the planets were on. And after that, very little happens in topology until 1895, when Poincaré begins the field of algebraic topology in an amazing paper called Analysis Situs. In which he introduces, in some sense, everything we're going to do this semester and next semester, almost. So he wanted to know, so okay, what had happened in between was Riemann and Betti had talked about connectedness. So, of course, people already understood about a space being connected or being disconnected. But Riemann wanted to go a little further. He was looking at surfaces. So a surface is something that locally looks like you're on the plane, but of course globally can be curved, right? So if you imagine somebody living on a sphere, it would be easy to do. You can imagine that this person, by only looking around them, would think that the world is flat, right? So anything where somebody could, just looking around, think that the world is flat is a manifold of whatever dimension that flat is. And so, in particular, a surface is a two-dimensional manifold. And what Riemann wanted to know was the complexity could be described by how many curves can you remove without disconnecting it, right? So obviously, if you pick a bad curve, if you were to pick a curve around the neck there and you remove that, well, you've disconnected it. Okay, don't do that. Instead, you can put a curve around here and a curve around here, and you can remove both of those, and now you have boundary, but it's still a connected space, right? And so the maximum number of curves that you could remove is what we call the genus of the surface, right? That name comes from Abel, not from Riemann, but whatever. That's what Riemann was studying, and Betti generalized that, and so we would denote it now as beta 1. How many curves can you remove from this without disconnecting? And what Betti did was he generalized this to higher dimensions. So if you have a three-dimensional manifold, so something that locally looks like R3, then you could look at surfaces, so two-dimensional things sitting inside it, and ask how many two-dimensional surfaces, without boundary, can I remove before I disconnect this three-dimensional guy, right? And that would give you beta 2 of a three-dimensional manifold. Beta 1 you can't define like this, because if you're in 3 dimensions and you remove a circle, you're not going to disconnect anything. But you can ask how many circles can I find that are disjoint and that do not form the boundary of a surface that lives inside this, right? So in general, beta m is how many m-dimensional pieces can we find that are not the boundary of an m+1 dimensional piece. Right, so the answer to that question is denoted beta m. Right? So this was where topology was between Euler and Poincaré. And Poincaré wanted to know, let's say we have a manifold and we have these numbers. Does that determine the manifold in some sense? Right? So you'd want to know does it determine it topologically? Does it determine it up to a continuous transformation? And that was the problem he set himself in this paper. So he started thinking about about finding pieces that were boundaries of other pieces or were not boundaries of other pieces as a way of finding holes, right? So you can think here we identified the holes in the surface by seeing how many curves we could remove without disconnecting it. So Poincaré came up with another thing you could do. You could think that you draw a loop on this space, and then you just try to contract it as much as you can, right? And it could be that you're on the sphere or something, and you draw your loop however you like, and you can always contract this until you're down to the point, right? And so you can think of it as like a lasso, and you pulled the taut, and you didn't lasso anything. On the other hand, over here, if you try to pull it taut, it's going to get caught on this hole, right? And so Poincaré thought, this is another way that we could look for holes. And so it should be measuring roughly the same thing as this, because they're both looking for holes, but it's a different way of doing it, right? So this leads to what we will soon be discussing, and it's called the fundamental group of a space. That is, you look at all of the loops starting at some point, starting and ending at a given point, and you can put these together into a group, and that is the fundamental group, right? So you allow a continuous deformation so that you can tighten them up as much as you can, and as a fundamental group. And he answered this question in the negative by constructing three-dimensional manifolds that had the same Betti numbers, so the same connectedness numbers, but different fundamental groups. And he showed that manifolds that can be obtained by a continuous deformation would have the same fundamental group, right? So by introducing some algebra into the question, he was able to answer it. And so that's the topic of our class, is algebraic topology, studying topology with algebraic invariants to try to answer questions like the one Poincaré was asking. So can you determine a space by these invariants, right? And the answer is no. The answer is always no. But the questions are very interesting. Now Poincaré himself did not put in all the algebra, did not realize all of the algebra in the constructions that he was carrying out. That was left to this wonderful mathematician, Emmy Noether, 1926. So she realized that what Poincaré was doing when he was studying Betti's connectedness numbers, of trying to find boundaries, pieces of the manifold, and whether or not they're boundaries of higher dimensional pieces, he was defining groups, which we now call the homology groups. Also, it turned out Poincaré's paper was wrong. Poincaré's papers were almost always wrong because he did not believe in revising. So he would just write down one go, send it in, and that was it. But he would make the most interesting mistakes. So there's this wonderful story about the article that he wrote for Acta Mathematica. So this is the journal started by Mittag Leffler in Norway. And to start the journal off with a bang, he had the king sponsor a contest where they were going to set some mathematical problem. Whoever solved this problem was going to get their paper published in the journal, and they were going to get some big award and handshake from the king, and wonderful. And now, Mittag Leffler wanted to make sure that it was a big name that won, because you want publicity for the journal. So he got together with the other two judges, Hermite and Weierstrass, and they thought, okay, what is Poincaré working on now? So here are 5 things Poincaré is working on. Okay, the contest is whoever solves one of these 5 problems gets their paper in the journal. And yeah, Poincaré won. But the problem he won with was on the stability of 3 bodies with Newton's law of gravitation. And And Mittag Leffler, it is a very hard article to read. The referees, which were the three judges, quickly dropped any pretense that they didn't know who the author was and started sending letters to Poincaré. We don't get this. How do you do this? And Mittag Leffler had one of his grad students try to understand the paper. And this grad student, whose name unfortunately I can't remember, got stuck on something and kept bugging Poincaré. I can't figure out this step. And eventually it turned out Poincaré was wrong, grad student was right, and the reason was that nobody had invented chaos theory yet. And so Poincaré invented chaos theory in trying to correct the mistake in his article, his award-winning article. The award had already been awarded on the stability of the three-body problem. So that was typical for Poincaré. He was brilliant, but lots of mistakes because he did not revise anything. So in particular, this paper is not as long as the supplements of the paper. So he wrote 5 other papers explaining mistakes he had made in this paper that are included with this one if you find a translation. And so in particular, he notices that actually to proceed like Betty was doing and to use submanifolds to find whether or not something's a boundary is not good enough. Manifolds are just not as well behaved if you want things to be embedded. To get a good homology theory in modern language from them. So he ended up using things much more coarse, as we'll see later, to define the homology groups. It wasn't until much later with the invention of cobordism and even later with stratified spaces that homology, regular homology, was realized using submanifolds. So that's in one of the supplements. And also the correction of the fundamental definition of the fundamental group is another one of the supplements. And the final supplement, somebody pointed out to him that he was implicitly assuming that a space with trivial connectedness numbers was a sphere. And so he realized, he came up with a counterexample for that, but then he decided, well, maybe the fundamental group is the only thing you have to check. So he conjectured that any space whose Betty numbers were trivial and fundamental group was trivial had to be a sphere. And then he decided, okay, maybe only in 3 dimensions, right? And so this is the famous Poincaré conjecture that was only resolved very recently using very high-powered tools in geometric analysis. But yes, he was right, but it was not trivial. And that's in the final supplement. Okay, wonderful. So Emmy Noether then introduced homology groups. And fun fact, when you study torsion in algebra, and this refers to elements of finite order in a group, right? The word torsion doesn't make any sense in algebra. And that's because it comes from Emmy Noether studying topology. And so it makes sense, or it made sense at first in homology groups, because it had to do, the canonical example was the Mobius band. And as you know, the Mobius band is like a strip of paper that you turn over and connect to itself. So it's the torsion in the geometry that's giving you these finite rank elements, finite order elements. And so that's where the word comes from for finite order. But so Noether revolutionized how we think about this, and all of the notions of functoriality or anything that's systematic about it comes from her contribution. And that really colors how we study it now. Finally, let me just back up. Right before Poincaré, Felix Klein and his Erlangen program. (1872). So back then, whenever you were made a full professor in Germany, actually for all I know it's still happening, but we don't do that here, fortunately. Anytime you were promoted to full professor, you had to give a public lecture to the entire university and any interested person who wanted to drop by. And some of these are fantastic. Most of them are extremely boring. Felix Klein, though, when he was made a professor at the University of Erlangen, he gave this public lecture, and it's now known as the Erlangen program. And he systematized geometry by saying that it's all about symmetries. So different types of geometries are just different symmetry groups that you're interested in. Just groups, so you're studying invariants that are not changed by any one of these symmetries, right? And that determines what geometry. Felix Klein is also the guy who showed that there's nothing to worry about with non-Euclidean geometries, right? And he did this by showing that, for example, what we now call spherical geometry is the geometry of the sphere in Euclidean space, and that hyperbolic geometry is just the geometry of the disk properly interpreted in Euclidean space. And so he showed that if you believe Euclidean geometry, you have no choice but to believe non-Euclidean geometry, right? So, but he continued this notion of putting non-Euclidean geometry at the same footing as Euclidean geometry with this Erlangen program. And so, for example, here he defines Euclidean geometry as the study of those invariants that do not change under translations and rotations. Right? And in this program, he also defines topology as the study of those invariants that do not change under continuous transformation. Okay? So that's what we'll be studying this semester. Okay? Any questions? Okay. Okay, so more concretely, we will be studying chapters 0, 1, and 2 of Hatcher's textbook. And chapter 0 is more like important notions that are good to have, but that don't really come into the general story of the other chapters. So I'm going to go over some of chapter 0 today. And I'd like you to read through chapter 0 when you find the time. The things I'm going to talk about today will be useful right away. The other things will be useful later. Okay, so, right, so let's start with a reminder. A topological space is a set X with a distinguished collection of subsets. Let's do script U, which we call the open sets, satisfying three things. It contains the empty set and the entire space. It's closed under a finite intersection, and it's closed under arbitrary unions. All right, so if you have two open sets, then the intersection is open, and if you have an arbitrary collection of open sets, the union is open. All right. A function A function is continuous if and only if the inverse image of an open set is an open set a bijection that is continuous and has continuous inverse is known as a homeomorphism. This word was introduced by Poincaré, and it means has the same parts. And topology is the study of those properties of a space that are not changed by homeomorphism, or that are preserved by homeomorphisms. All right, so in some very abstract Aristotelian sort of thing, the ultimate object of topology should be to classify spaces up to homeomorphism. So what you do is to show two spaces are homeomorphic. You want to exhibit a homomorphism. So for example, if you want to show that an interval and the real line are homomorphic, you might do stereographic projection. Right? And so you would just roll the interval up and then define a map like so. Right, and write down a formula for the map and a formula for the inverse, and see that they're both continuous, and conclude that you have a homeomorphism. On the other hand, to show that spaces are not homeomorphic, you look for an invariant, obviously topological, that is different. So, for example, the set 0, 1, union 2, 3, and the real line, well, you would say this one's connected and that one is not connected, and so they can't be homeomorphic. For 0, 1, and the closed interval 0, 1, you might say, well, this one is open, this one is compact, so they can't be homeomorphic. Right? For, say, the circle and the closed interval, you might say, okay, well, they're both connected and they're both compact, but if I remove a point from this one, I can disconnect it, whereas no matter which point I remove here, it stays connected, so they can't be homeomorphic. Right? So what we're going to look for is algebraic invariance. Okay, so our convention, to save on chalk, is that all maps, all spaces are topological. And all maps continuous. Okay, so unless otherwise stated, you can assume those words are in the hypotheses. Okay, so even though the fundamental objective in the background is to classify spaces up to homeomorphism, it turns out that the invariants we're going to define are invariant under a weaker notion of equivalence, and that's the notion of homotopy equivalence. So it's useful to have a weaker notion of homotopy equivalence. And everything we're going to define in this course, and this semester and the following one, so the fundamental group, homology, cohomology, and then higher homotopy groups, are actually invariants up to homotopy equivalence, not just homeomorphism. So if you want to tell spaces apart and they're homotopic, then you need to use stronger invariants. So there are things you can do with these invariants. You can twist homology with local coefficients. So you take into account how the fundamental group acts on the space, and it's something called the universal cover. Or you need to use stronger invariants. OK, so one example is if you have an annulus and a circle, say sitting inside it, then you can continuously deform the annulus until you get just a circle, right? So these are going to be considered homotopy equivalent spaces, although they are not homeomorphic. They're not homeomorphic because this is a one-dimensional manifold and this is a two-dimensional manifold with boundary, but showing the dimension is a homeomorphic invariant was actually very hard in the history of algebraic topology. But it is. OK. So let's define a homotopy. A homotopy is a continuous family of maps. Right, by convention indexed by the interval. Right. And what we mean by a continuous family is that if you put them all together into a single function from x cross 0, 1 to y, right, so x comma t goes to f sub tx, this is continuous. Right? So this is what we mean when we say continuous family. Okay, so we say that F0 and F1 are homotopic and denoted like that, right? If the homotopy satisfies that f sub t restricted to A is independent of t, where A is some subset of x, then we say that F0 and F1 are homotopic relative to A. Right? So if you're doing a continuous deformation and there's some subset where you're not doing anything, then you say that the homotopy is relative to that subset. So in the example of the annulus deforming to the center circle, right, you could set up your deformation so that you're just moving every point closer and closer to the center circle, but points on the center circle wouldn't move at all, right, throughout the homotopy. And so that homotopy would be relative to the center circle. Okay. So the book likes to have like a thin letter and then a thickening of it. And so you have line segments connecting the boundaries of the thick letter, and you could put the same sort of homotopy by moving every point in the thick letter to the nearest point on the thin letter, and you would end up with a homotopy relative to the thin letter, because that would just move it all. Right? So it's the same. You could think that the annulus is just the letter O thickened up, right? So, this sort of homotopy gets a special name. So remember that a retraction is a map such that R squared is equal to R. So that's the topological version of a projection. So it's like well, that's a fair point. Let's make it X. Sure. But so in particular, the since R of X is equal to R of X, then R acts as the identity on its image. Right. So indeed, as you pointed out, it has to go from X to X so that we can say that it is the identity on its image. So in this case of the thickened letters, the retraction is just to every point in the thick letter, send it to the nearest point on the thin letter, right? And so points on the thin letter are just going to stay put. Right? So it is a retraction. Now, every space has a retraction to a point. Just take all of the space and map everything to a point. Right? So just having a retraction doesn't tell you much about the space. But what's special about this one is that you go from not doing anything to the retraction, to mapping everything onto the thin letter. Right? So that is called a deformation retraction. So a deformation retraction is a homotopy from the identity to a retraction. So let's say ft from x to x with f0 is the identity of x, f1 is equal to this retraction, and we're going to impose that f sub t restricted to r of x is equal to the identity for all t. Right? In other textbooks, this is not included, and when you include it, you say you have a strong deformation retraction. Right? And deformation retraction is just up to there. Right? So the main example is these letters, right? That's what we're doing because throughout the homotopy, the subset, the thin letter, is not changing at all. Another example, which is the same idea, is take Rn and the origin and just define ft of x to be tx. So this would be ft from Rn to Rn. Right? So when t is equal to 1, well, it's going in the opposite order, but that doesn't really matter. When t is equal to 1, you have the identity. When t is equal to 0, you have the map to the origin. And throughout the homotopy, the origin is fixed. Right? So it's a deformation retraction of Rn to a point. Okay. In this case, we say that the origin is a deformation retract of Rn if we want to say that there is such a map, a homotopy, without having to specify it, to bring in more notation. Okay. Okay, so great. So one thing I mentioned in the history section was that originally Poincaré and Betty and all of these people were interested in manifolds, right? And once you're done with this course, you probably will care only about manifolds. But during this course, we allow ourselves to use awful spaces if it makes our life easier. And so we do that over and over. We might have a function we want to study, and we decide to take that function, possibly complicated function, and put it into a space so that we end up with very simple functions, but complicated spaces. Right? And as long as the spaces aren't too complicated, we don't care. So here's one example of that. Here's a construction called the mapping cylinder. Of a map between topological spaces. So this is denoted M sub f, and it's what you get by taking the cylinder over x and then gluing it onto y by deciding that one of these endpoints, I think in the book we glue at 0. So the picture is that you have x, and you take the cylinder over it. And then you have y, and then inside y, you have f of x. Right? And what you're going to do is glue this bottom copy of x onto y along this image. Right? So of course this image, we're making no assumptions on f. This image could be absolutely horrible. Right? It can crisscross, it could be sine of 1 over x. Right? It could be absolutely horrible. But that's okay. We glue it on. So let's say that it's not so bad and it ends up looking like this. Okay, so there are some obvious properties of this space. One is that has a deformation retract onto y, right? So if you want to deform all of this space to y, just collapse the cylinder, right? So just map everybody along this interval, right? Question?
I was just going to ask if you could explain what's going on in those pictures again. I'm a little confused.
Yeah, OK. So we have two topological spaces. Okay. And we're going to glue them together to form another topological space by just identifying some points here with some points there. Right? And so what we do is we say, OK, look at the bottom point, every one of these points. I'm going to identify it with a point in y. Which point in y? Well, wherever f wants to send it. Right? So you have some curve here, and you just identify it like that. Right? So where it got identified, it can look absolutely horrible. Right? This could be a very nice, smooth space. But once you glue it on, it's terrible. Right? If you want to work out an example, just think that you have the circle, and that your map is think of the circle as lying in the complex plane, and think of your map as just the square. So it's just rotating you around twice. Right? And then think about what this would look like after you glued it. Yeah, so you end up with a space that looks a bit horrible here, right? But it has some redeeming features. One is that you can deform it continuously onto y, right? And you can do that easily. You're just pushing this cylinder down, right? So your homotopy would just be move everybody along the interval, right, until you end up in y. So it has a deformation retract onto y. And another nice fact is that it has a map. We have a map. From here to y, induced by so if you give me, OK, so I'm going to define a map on the mapping cylinder. And the way I'm going to do that is I'm going to define what you do on this piece and what you do on this piece. And as long as we're doing compatible things on the points we've identified, then it's well defined on this space, right? So what you do on this piece is you map it to f of x, right? And then what you do on y is nothing. Right? So in both cases, you end up in y. Right? We could go ahead and close this. So here, you just ignore the interval, and you send it to f of x. And here, you just don't do anything. Take as the identity. Right? So what happens on points that we've identified in this space? They better have the same image for this to be well defined, right? But of course, if you have x comma 0, you send it to f of x, and it gets identified with f of x here, which gets sent to f of x, right? So it's well defined. OK. But moreover, notice that this is exactly the retract that you get at the end of this deformation retraction, right? Because you're just identifying, when you push this down, you're identifying everything lying above an x with f of x, right? So this is the retraction. In the deformation. OK, and then f as a map, let's write it like this. F is a map from x to y, we can factor as include x into the mapping cylinder, and then apply this retract. So this shows that every continuous map factors as an inclusion, you could say an embedding, followed by a retraction, and not any retraction, but one from a deformation retract. Okay? So for some things, and this would be very useful in the algebraic topology part 2 especially, but for some things you can take any map. If you want to prove something about continuous maps, it's enough if you can prove them for inclusions and retractions. And not arbitrary retractions, but coming from a deformation retract. Right? So we get that reduction of the things we need to prove by allowing ourselves some awful spaces like this one. Okay? Okay. A deformation retraction is a nice example of a homotopy equivalence. Okay. This refers to a map such that we have another map going the other way. So we're going to take the notion of homeomorphism and we're going to weaken it. Right? So homeomorphism, you have a map going one way and a map going the other way, and when you compose them, you get the identity either on x or on y. Right? So because, as we said, it's a bijection that's continuous with a continuous inverse. Right? So in this case, we're not going to demand that when you compose them, you get the identity on the nose. We're going to demand that when you do f composed with g, so this would go from y to y, this is homotopic to the identity on y, and g composed with f, which would go from x to x, is homotopic to the identity on x. Okay, so they're not equal, but they are homotopic to the identity. Right? So, for example, well, as I said, any deformation retract, but let's say Rn and a point are homotopy equivalent, where you have the inclusion of the point into Rn, and the retraction that we, well, here, the retraction is to send everybody to 0, right? And the fact that the composition is homotopic to the identity is the fact that this retraction is the end of a deformation retract, right? The deformation retract is precisely the homotopy to the identity. Okay. If a space, okay, if x and y okay, is a homotopy equivalence. So if you have a homotopy equivalence between spaces, then we say x and y are homotopic. And we write homotopic like that, right? If x is homotopic to a point, we say that x is contractible. Right? So contractible spaces are trivial spaces as far as homotopy is concerned. Okay. We also say that x and y have the same homotopy type. Okay. Okay, so that's one of the fundamental concepts in Chapter 0 that's very useful. Our first real topic is going to be the fundamental group, and that's all about homotopies. This is what we were talking about taking a loop and thinking of it as a lasso that you tighten. So that tightening is precisely taking a homotopy. Right? So we're going to be interested in homotopy classes of loops in a space. The other fundamental notion is what's called a cell complex. So here, this is a generalization of identification spaces for surfaces. So how many people have seen identification spaces for surfaces? Well, you're lucky. You can look forward to learning about identification spaces for surfaces. But OK, so it's really cool. OK, so the study of manifolds, similar to how we just said that for topology, your fundamental problem should be classify all topological spaces up to homeomorphism. If you were doing geometric topology, so that you're studying manifolds, your equivalent problem would be identify all, let's say, smooth manifolds up to diffeomorphism, right? So a diffeomorphism, of course, is a smooth map with a smooth inverse. And so, OK, for one-dimensional spaces, that's trivial, because if they're connected, then you either have the interval, half line, or a circle, right? But when you go to 2 dimensions, it's more interesting, but it turns out to be completely solvable. All that matters is the genus, so how many holes do you have, and whether or not it's orientable. Right? And that completely determines the surfaces. And what's fascinating is that that's true no matter how you're thinking about surfaces. If you're thinking about them algebraically, as complex manifolds, as real manifolds, as topological manifolds, they're the same, and they're completely classified by those 2 invariants. Right? And one way of showing that is by constructing them from classifying spaces. So what you do is you think of this as being triangulated. So you have lots of triangles on the surface. And then you cut out all of those triangles and you lie them flat on the table. And then you start saying, OK, well, on the surface, this edge was identified of this triangle was identified with this edge of this triangle, so I'll glue them together. And you keep gluing them together, but keeping flat. You don't allow any curving, right? But you remember where all of the sides were identified with other sides. And what you will end up with is a polygon. If you do things as efficiently as possible, you will end up with a polygon with certain side identifications, and that gives you the surface. And then it's OK. So let's look at this for example. So I'm going to say this side is identified with that side, and this side is identified with that side. So this is just like playing Pac-Man. But if you wanted to go back to the surface, you would say, OK, well, I should identify this side with that side. So that means that really I have something that looks like this. Right? There's B, where I've identified them. And then here, this keeps its label A to remind us that those should be identified. Right? So now we want to identify them. OK, so we have to twist this one over and glue it over there. And so what we end up with is a torus. right? And so this, this space is one way of representing the torus. If you have, say, a genus 2 surface with that's orientable, then the corresponding space, the polygon you would end up with, is I should have 8 sides, which I may or may not be able to draw. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8. There we go. And the identifications are like this: C, D, C, D. And over here, if you were to take this point and do identifications like this, and then keep track of what happened to these curves, you'll find that, well, A is going around this hole this way, B is going around this hole this way, C is going around like this, and D is going around like that. Right? So these identifications, of course, have to do with the holes in the surface, the parts that don't line up flat. Right? So, excellent. Well, just to finish the story, so for 2 dimensions, you can do everything, right? Then for 3 dimensions, the Poincaré conjecture was asking, okay, well, can you even identify the sphere just by knowing that the topological invariants are trivial? And, well, even for the sphere, that's hard. Fantastically, it turned that before we could do dimensions 3 or 4, Smale was able to do every dimension higher than 4 at the same time. So that's amazing. It's a fantastic part of topology. It's called surgery theory. And so it's sort of similar in that you're building up manifolds by attaching handles as opposed to identifying sides. So it's sort of like a smoother version of doing this. And then he got into a little bit of trouble because he got a big grant, and so he went to Brazil and he worked it out, this big theorem, while he was on the beach and of Rio de Janeiro. And he gave an interview where he admitted this, where he bragged about it, and then the NSF was somehow upset that he was spending his grant time at the beach. But you know, if you can do surgery theory. Let's all go to the beach. Great. Then dimension 4 was this fantastic result of Friedman, where it turned out that whether you were classifying things smoothly or topologically was completely different in dimensions 4 and higher. And then dimension 3, it wasn't until the proof of geometrization and the by Ricci flow that we got even the case of the sphere. But this notion of identification spaces, well, and I should say that even for dimensions 4 and higher, you can only hope to classify manifolds within a given homotopy type. Because if you could classify all manifolds, you'd be able to classify all fundamental groups. But any finitely presented group appears as the fundamental group of the manifold of dimension 4 or higher, 4. So 4 or higher in particular. Then, so you'd be able to classify, you'd be able to solve the word problem. And the word problem is undecidable, so you can't do it. But within the single homotopy type, there is surgery theory, and it's very cool. And it sort of grows out of this. But I'm going to save the rest of this discussion until next time. So I'll see you on Thursday.